I mean, technically, Ohio is an interesting state where you don't have to do that. It's single party permission. So if you're recording somebody, you normally don't have to let them know. But I think for school purposes or people under 18, you do. All right, so this is circuit 3. It's got a lot in it. Resistor 1, 2, 3, 4, 5. 20 ohms, 20 ohms, 8 ohms, 15 ohms, 15 ohms. So one of the first things I like to do is redraw a simplified version of the circuit. So here on the right side, I've got a 15 ohm resistor, and in this part of the circuit, these two are in series with each other because the only way to get from here around to the other side is through both of them. So since they're in series, that's an equivalent 30 ohm resistor. When I think about that now, this is a 20 ohm in this middle branch. All this on the right side is 30 ohms. So I use the rule for parallel circuits, which basically is 1 over R1 plus 1 over R2 is equal to 1 over the equivalent resistance. So when I do that, it's 1 over 30 plus 1 over 20. That actually reduces down to 1 over 12. It doesn't have to be a nice even fraction. If it's a decimal, that's fine. And we just take the reciprocal. So that's 12 ohms for all this stuff. So for all this is 12 ohms. So now I've got the super simplified circuit, and it's easy to figure out the total resistance. 20 plus 12 plus 8, because that's how we figure out resistance in a series circuit. So I'm going to move this again off to the side. I'm going to do my work over here where I think you can see. So almost always the first thing you want to do in a circuit is figure out the total resistance. So we just figured out this is 20 plus 12 plus 8. So that's 40 ohms. The total current is equal to total voltage divided by total resistance. So 12 volts, 40 ohms. 12 over 40 is a little more than 0.25, 0.35? No. 1240 divided by 4. Yeah, 0.3. So Zach and Daniel and Justin, what that means is I've got 0.3 amps coming out of this power source. That 0.3 amps is passing through here, but then here it's going to split. So with Kirchhoff's junction rule, whatever the total is coming into the junction has to also equal the total leaving, but now it's split into 2 branches. So when I look at the next parts of this, it's asking me the voltage across R1 and the current through R1. So the current through R1 is just the total, because there it's a series circuit. So that's 0.30 amps. I can use Ohm's law, which is V equals I times R, to figure out that 0.3 amps multiplied by 20 ohms is equal to my voltage, and that's going to equal 6 volts. The next part is actually asking about R2, but I don't want to do that yet. This is all by itself, so it's probably easier to solve. So that's what I'm going to do next. So the voltage across R2 is going to be up here. Current through R2 is here. Voltage across R3. Current through 3. Voltage across R4. Current through R4. Voltage across R5. Current through R5. So the current through R5 is also going to be the same as the total current, because at this part of the circuit, there's only one path as well. So that's 0.3 ohms. So if I want to figure out the voltage across that, or 0.3 amps, pardon me. Don't forget, you can correct me when I screw up. 0.3 amps. This is 8 ohms. 0.3 times 8 is 2.4 volts. So I'm left with these ones now. I think I want to think about this particular part of the circuit, this simplified circuit. So whether you go from this top part to the bottom part through the middle branch or this outside branch, you still got to lose the same amount of voltage. And there's a couple ways to think about that. One would be, we know that across here, we've got a voltage of 6 volts. And we know that across here, we had a voltage of 2.4 volts. Well, the circuit or the battery can only give 12 volts. So if we did 12 minus 6 minus 2.4, that would tell us the voltage across this equivalent resistor. The other way you could think about it is to think about the fact that this whole part of the circuit acts as a single 12 ohm resistor. And even though the current is split between the middle branch and the outer branch, when we think of it as one equivalent 12 ohm resistor, we would still have the total current of 0.3 amps going through. So I could say for R3, I could think of the fact that I've got 0.3 amps total equivalent times 12 ohms. And I know this says 20, but the idea is voltage is the same across any entire branch that we've got. So I'm going to say 12 ohms. And that should be 3.6 volts. The other way you could have thought about it is the 12 total minus 6 minus 2.4 also equals 3.6 volts. So you get the same answer to either of these methods. So now I could think about the fact that what's the current through this? Well, the current is delta V over R. The voltage across that branch is 3.6 volts. The resistance of that branch now, I'm only focusing on that branch, is going to be 20 ohms. So that should be about 0.18 amps. These two are the last two I'm going to hit. The voltage across each of them is going to be less than 3.6 volts because in this outer branch, even though this branch is in parallel with this branch, there's two resistors in series with each other here. So their total voltages have to add up to 3.6 volts. The easiest way I think that I can figure this out is I want to figure out the current through this branch first. So the current through this branch would be the total voltage across the whole branch, which I just figured out is 3.6 volts, divided by the whole resistance of that branch, which is 30 ohms. So I'm going to say this is 3.6 volts over 30 ohms. I think that's going to be 0.12 amps. Now, if I did my math right, the current through this branch and this branch should add up to the total. Our total is 0.3. The rightmost branch is 0.12. The middle branch is 0.18. Those two currents do add up to 0.3 amps. So I'm good. Since resistor 4 and resistor 2 are in the same path, once I know the current through this, it's the same as the current through the other one. So I don't need to do any work for that. Now finally, I'm going to go back here and I'm going to figure out the part of the 3.6 volts across this resistor and across this resistor. So I'm going to go back to Ohm's law, I times R, 0.12 amps. And this resistor is 15 ohms. So that should be 1.8 volts. This is going to be the same because it's also 15 ohms. And if I'd noticed that before, I could have known that this was going to split equally 1.8 and 1.8. Because if I have 3.6 volts across this entire outer branch, and half the resistance is here and half the resistance is here, half of the voltage across that branch, which was 3.6 volts, would fall across this, and the other half of that total voltage across the branch would fall across this. So Zach and Daniel and Justin, I wish I could say that there's one way to attack a circuit. There's not. If you try to memorize a particular path, it definitely is not helpful. But the big idea is Ohm's law is applicable to all parts of a circuit and the entire circuit. And you've kind of got to zoom in and then zoom out to decide, are you thinking about a particular branch, particular component? I really like redrawing circuits because it helps me think about things better if I have maybe 2 or 3 diagrams for a complex circuit. So for example, this made it really easy to get the voltage across this whole part of a circuit. So I did record that and I'll upload it to our Google Classroom because that's a lot, right? This is not trivial. So at any rate, that's kind of how I would go through that one. I'll upload an answer key to these other ones also, Zach, and or I'll send it to you because my other cohort gets them next week. Mm-hmm. And what I'll end up doing is we'll find time where you and I can go over anything you need to, okay?
All right.
I really appreciate you tuning in today. I'm not saying you're better than Tanner Pope, but you're better than Tanner Pope. Yeah, just say it. Just say it.
We're recording.
That's cool. Oh, that's right. I'm not allowed to say that on a recording. Of course you're not. Well, audio difficulties. So I'm not sure what is going on with him. So I'm going to stop recording now, and I think they've got to clean up.